Hello, class. I certainly hope. I'm looking at the thing here. Everything looks pretty good. It is Monday morning, and I've put two other lectures on the Scott Grenquist YouTube channel. And today what we're going to do is we're going to talk about an RL circuit rather than an RC circuit. And a lot of times during these lectures, you're probably wondering why I take so much time talking. And spaces in between the time talking. I'll tell you why, because I'm sitting here in my house. On the first floor of my house, I'm on the ocean down in Hull, actually the bay side. And the whole back of my kitchen here is glass. I'm doing these in my kitchen. And I look out onto the bay, and then I look out onto World's End, State Park across the way, and it's just a beautiful setting. I love this house. I loved it so much. I just bought the four-family, or I'm in the process of buying the four-family next door. Now, after having said that, so that you can understand, I also have music going in the background that I'm listening to every once in a while as well. So I'm multitasking. Now, what we want to do today, and we are getting toward the end of what really the instruction for this course is. And that's because I pushed you a little faster than we should have when we were all together. And you're probably thinking, oh, did Professor Grenquist know we were all going to be sent home for the coronavirus thing? Of course I didn't. Let's just say that anyway. But we're getting up to a point now where you're starting to see the applications of the various different concepts and fundamentals that you've learned, both for the DC and for the AC. The only thing that we really have to go through now, we've gone through the RLC, the voltage maker circuit. That was 2 lectures ago. We've gone through the RC low pass filter, and with the CR circuit, I usually in class would go through the CR circuit and basically explain that it's just the opposite of the RC circuit, right? And so instead of it being a low pass filter, it's going to be a high pass filter. So what we're going to look at this time is we're going to look at the RL filters. I say filters because just like an RC circuit can have can be a low pass filter, an RL circuit can be either a low pass filter or a high pass filter, just like an RC circuit. We don't use RL circuits all that much. There are some specific applications where you would want to use an RL circuit rather than an RC circuit, but not really many that I could think of off the top of my head. And like I say, most of the, if we wanted a band pass filter, we would use an RLC circuit and then set that up for resonance. Like the lecture that we had a couple times ago where we talked about the resonance in that RLC circuit. So we've done that. The last one I want to cover really is more for the academic understanding of what the impedance is for and why they're backwards. If you remember, I said that an RC circuit, and that would be the resistor first and the capacitor second. An RC circuit is a low pass filter. And of course, the way that I remember that is because RC was a low quality cola, right? And then a CR circuit is going to be a high pass circuit. And that's all you've really got to remember, is that the RC is low. And then you just do these around. So the RL is going to be a high pass circuit, and the LR is going to be a low pass circuit. And when we look at these, we can see, a low pass circuit would let the low frequencies through, and then um, so low pass. And of course, this is going to be frequency down here, and this is going to be, let's say, voltage. Voltage at A is what we called it. So we'll say voltage at A. Of course, voltage at A in this is really the same as the voltage across the capacitor, isn't it? Since that capacitor, one end is hitched to ground and the other end is hitched to the point A, right? If we had the high pass filter, well, that's just the opposite. That means that it dampens out all the low frequency stuff and then allows the high frequency stuff to get through. Now, on a telephone, or on the old style telephone, not your cell phone, although actually the instrumentation in a cell phone would do predominantly the same thing that your regular home phone had, and that was a limitation on the frequency bandwidth from 30 hertz up to about 3,300 hertz. And that was the bandwidth of a telephone communication system, and of course, or your home telephone communication system on the trunk line. And of course, what that did was it meant that really high frequency stuff could not be transmitted through there. And of course, in our digital age, using fiber optic and all digital communication over the trunk lines and everything, we can send much higher things. In fact, I could download a video that had a wide range of frequencies, couldn't I? So we're not limited to that 30 hertz to 3,300 hertz like we were 15 years ago. I have a delicious cup of coffee. No, it's not an espresso. Where am I going to get an espresso from? Who asked that? Now, let's go back to, and this is a high pass filter. And again, that's my frequency, and that would be my voltage at A. So let's look at the circuit that we're thinking about here. So the circuit that I'm going to look at, this is going to be for a high pass thing, and we're going to look at why this would work for a high pass and not a low pass. We looked at the low pass before with the RC circuit, and I can point out pretty much immediately why an RL circuit at point A would have just about the opposite type of response, frequency response, as an RC circuit. I think we can see all of that in there, because let's just look, and I just write these over and over and over again, don't I? So Z sub R is going to be R plus J0 ohms, right? Z sub L is 0 plus J omega L ohms. Notice where omega is. Omega is in the numerator for the impedance of an inductor, isn't it? And how about Z sub C? Z sub C is 0, and then I'm going to put the plus J, and then I'm going to make it minus 1 over omega C ohms, right? So we can see that not only is this negative, and that's positive, but we can also see that the omega is in the numerator here, and omega is in the denominator here. And of course, that really explains everything. So as the frequency gets higher for a capacitor, that means that the denominator is going to get larger, so the reactance is going to get smaller, right? Let's not forget what Z is. Z is resistance plus J reactance, right? So that's going to get smaller, but in the numerator, it's going to get larger. And of course, that explains the reason why these are backwards. RC is a low pass, but then RL is a high pass. And that all has to do with the fact that omega is in the numerator for the inductor, and it's in the denominator for the capacitor. All right. What is omega? I would say, I would call on somebody to give me that, but of course there's no calling on anybody here. So omega is 2 pi f, and of course those are radians per second. Remember how we got those radians per second. 2 pi radians per cycle times f, and f is cycles per second. You're probably thinking he's going to ask us about that on the final. He's going to ask us if what the real units of f and 2 pi in omega are, isn't he? That's what he's going to do. I don't know. I may not. But if I were you, I would definitely prepare for that eventuality, right? Now let's get back to this and let's look at what I've got. Now originally I said that that was 5,000 ohms, right? And so we wanted to look at how L would compare there in 3 different instances: a very low frequency, a resonant frequency where both the real resistance of the resistor equals the imaginary impedance, or I should say the reactance of the inductor, right? So that's what we want to look at. That's the second thing. So let's look at these. So first, low frequency. Second, we want to look at the resonant frequency, right? So where these two would be the same. I'm not really going to call that resonant frequency. You know, I really am using the wrong word here. The resonant frequency usually in a circuit is where you have an inductor and a capacitor, and the inductance, which is positive, cancels out with the capacitance, which is negative. That's real resonance. All I'm putting, all I want to put here, and I should probably use a little different terminology, is when the phase shift angle is going to be at 45 degrees, because the resistance and the reactance of the inductor are going to be equal to each other, and that's really where the phase shift is at. I'm going to put that down there. The phase shift equals 45 degrees at that point, doesn't it? And then the third thing that I want to look at is high frequency, right? High frequency, and how's that going to change things? So the first thing we want to do is we really want to find out, well, let's give the inductor a value here, right? So let's say that I have I'll say a 1 Henry, right? So that the mathematics works out better that way. So let's look at 3 different things. We've got the 5,000 ohm, that's the resistance, and then we've got an inductor which is at 1 Henry. So if I said, okay, low frequency, let's say that we're at 100 hertz. Okay, 100 hertz. So we know that omega is then going to be, let's just write omega out here. Omega equals 2 pi radians per cycle times the frequency, which is going to, in this case, be 100 hertz. And that's going to give us 628.3 radians per second, right? That's what we've got. So if I were to multiply that by 100, because let's remember what it is, it's omega L, isn't it? So omega times L, 628.3 times 1 gives me 628.3 ohms. So we know that R in this case is going to be 5,000 ohms, and we know that the reactance of the inductor is 628.3 ohms. If anybody doesn't remember how I got that, flip back 15, 20 seconds and you'll see. So you can see that that's quite different, isn't it? Right? R and L. And in fact, if we wanted to find, I'm just going to put this here and do some calculations over here where you can see them, and I can still keep this wide open. So let's do that. What is the total then impedance? And I think everybody can see that 628 compared to 5,000, you know, we square both, don't we? Don't we square the 5,000 and add it to the 628.3 squared, and then take the square root of the sum of the squares, just like in Pythagoras' theorem? So 5,000 squared plus 628.3 squared equals taken to the square root. And of course, we would expect it to be very close to 5,000, wouldn't we? So that would be 5,039 ohms at an angle. And how do we find the angle? It's the inverse tangent, isn't it? The inverse tangent of the reactance over the resistance. So the reactance, 628.3 divided by 5,000, and then take the inverse tangent of that, gives me 7.16 degrees. Oh, wait, I'm sorry, 7.16 degrees. Sorry about that. Where is that correct type? There we go. All right. So it was the right answer, just written in the wrong place. So there we go. So that's what our total resistance is. Now, let's go through that for a second. Let's say, okay, well, that's the total resistance, and it's about 5,000. So I, in this case, is going to be our 100 volts peak. So 100 volts peak at an angle of 0 degrees divided by 5,039 ohms and an angle of 7.16 degrees, right? So 100 divided by 5,039 gives me 19.85 milliamps peak at an angle of 0 minus that, so that'll be minus 7.16 degrees, right? So 19.85 milliamps at minus 7.16 degrees. That's our current. That's about 20 milliamps, isn't it? Close to 20 milliamps. Now, if that's our current, then what's the voltage drop across the resistor? So let's write that down. What's my voltage drop across that resistor? Well, that's going to be the current. So 19.85 milliamps. Don't forget to put the 19.85 times 10 to the minus 3. Don't work in milliamps. Always work in your primary units. I forgot to put the minus 7.16 degrees here. I'll put another parentheses around there. And then that's the voltage drop times the resistance of the resistor, which is 5,000 ohms at an angle of 0 degrees. So my voltage drop, I'll just put D. My voltage drop across that resistor, 5,000 times the current, is going to give me a voltage drop of 99.22 volts, and it'd be at an angle of minus 7.16 degrees. Why is it minus? Because that's a minus and that's a 0. So minus 7.16 plus 0 gives me the minus 7.16, right? So that's my voltage drop. So what will my voltage at A be? My voltage at A, if we went through the whole process, we would have to turn this back into, in fact, I probably, well, let's just do this. So it'd be 100 volts at 0 degrees minus 99.22 volts at minus 7.16 degrees. And I think everybody can see that, even if it's minus, it's predominantly all real. So 100 minus 99 is basically what you're going to get there. right? This isn't going to give us a large enough section where it's not. So this is really going to be 0. You know, if I wanted to actually write this out, why don't I do that? 99.22 times 7.16 cosine. You're saying, why didn't I put in minus 7.16? Well, 7.16, the cosine of 7.16 and the cosine of minus 7.16 is exactly the same. I mean, and I don't even want to write it down here, the unit circle, for you to see that. I want you to have that unit circle in your head, just like I want you to have the complex plane in your head. You know, I'm reading, from my time stuck in here, I'm reading Richard Feynman's lectures at Caltech on electromagnetic field theory, because I'm teaching electromagnetic field theory this summer. I teach it a lot. I love electromagnetic field theory. I love antennas. I love all those things. But where was I going with that? I don't know. I'll come back to that in a minute. Because I don't have Alzheimer's disease, I'll actually remember what it was that I was doing. Now, what was that about Feynman's electromagnetic? Anyway, I also put up one of the things on my YouTube channel too, if you want to look at that, for the electromagnetic field theory course. It's a discussion on Maxwell's equations and how that led James Clerk Maxwell to realize that light, and nobody thought that light was an electromagnetic wave. Nobody thought that until he worked out the math to do it. So it's an interesting lecture if you want to, you know, sit down and listen to that lecture on electromagnetic field theory too. Anyway, I know what I'm getting back to. Dirac. Yep. Dirac once said, I was going through this with the Richard Feynman lectures, and Richard Feynman pointed out that Dirac once said that you do not know what an equation really means until you can visualize that equation in real time space. And you know, when I was your age in college, I didn't really know what he meant by that, because how in the world can you see a equation? And only later did I realize, in having the unit circle inside my head and the complex plane inside my head and some other things inside my head too, and being an engineer, being able to manipulate things inside my head, I realized what he was saying, that you're right. Unless you can visualize the equation inside your head and its ramifications to the real world, and I don't just mean a real Earth, I mean, you know, the whole universe and how it would play out, or the microscopic, you know, universe of an atom, and that is what you should understand too. So think of the unit circle in your head. Think of the complex plane in your head. Do the things in your head. But I think everybody can see that minus 7.16 on the unit circle is going to have the same cosine as 7.16. All right. So now that I've gone on that soliloquy, I can give you this. This is 98.4 minus J. Why do I say minus? Because it's a minus 7.16, isn't it? So let's also do the imaginary part here, and that's going to be 12.4. 12.4. So 98. So you can see that 100, and this is really 100 plus J0, isn't it? And then I'm going to subtract off 98.4 minus J. Now that minus is a minus, so it'll be a plus. Remember that, 12.4. Now, if we work that all out, and I'm taking up more space here on my paper than I wanted to, but I think that everybody can see that 100 minus 98.4 is going to be 1.6, and 0 minus a minus J 12.4 is going to give me plus J 12.4, right? And so when we get to that point, 1.6 plus J 12.4, well, I think everybody can see that that's going to be very close to 12.4, isn't it? And it comes out to be 12.47, so 12.47 volts. And I could do the angle too, but you know, why? Because I've got the thing has gone down to 12.47. Well, that is this area, you know, that would be right here. That would be your 12.47 volts at A. Could we get less than 12.47 volts? Yeah, I could make this 10 hertz, couldn't I? And then if I made that 10 hertz, this wouldn't be 628.3, it would be 62.83, wouldn't it? Which would make it much smaller, and it would make it basically negligible. But in fact, in here, it's pretty much negligible too. All right, well, let's change the frequency now so that both of these are equivalent to one another. And before I do that, let's just look at if I were to make them equivalent to each other. Let's say that at resonance, R equals omega L equals 5,000 ohms, right? So if they both equal 5,000 ohms, then we're going to have 5,000 ohms, or if I looked at the total impedance in that series circuit, it would be 5,000 ohms plus J 5,000 ohms, right? I'll put the ohms on the outside. So if I wanted to find the total, and I think everybody can see that, if I square 5,000, I square 5,000, I add the two of them together, and I take the square root of that, oops, screwed that one up. Sorry about that. 5,000 squared plus 5,000 squared equals a lot, and then the square root of that is going to be 7,071. So 7071. There's that 7071, or 1 over the square root of 2, that keeps coming back at us over and over and over again, doesn't it? So 7,071 ohms at an angle I think everybody can see right on the complex plane. If I was just to draw the complex plane here, 5,000, 5,000. So I'm really, you know, at 45-degree angle, aren't I? And of course, that really, the phase shift angle at 45 degrees really lets me know that I am at, I won't, like I say, won't say resonant frequency here, but where the resistor and the inductor equal each other. Now I want to look at that because, you know, we've got a special frequency here too, don't we? We've got a special frequency where the resistor and the reactance of the resistance of the resistor and the reactance of the inductor are going to be the same. And that's a special frequency. So where would that actually occur? So let's do that. 2 pi f L equals R. Right? Isn't that right? Isn't omega L 2 pi f L equals R? And isn't that what we're saying at this special frequency that we've got here, where the resistor resistance and the reactance of the inductor are exactly the same? Well, let's find out what that special frequency is. We'll call it the cutoff frequency. And that would be R divided by 2 pi L. So let's do that. So I've got 5,000 ohms, and I want to divide that by 2 pi times 1 Henry. 5,000 divided by 6.283. And that equals 796 hertz. So my cutoff frequency here is 796 hertz. That's a very special frequency at which those two are going to be equal to one another. You're probably saying, where does that actually occur on here? And it occurs right there. It occurs when we look at VA equals 0.7071 times V sub S, right? 0.7071. When we looked at the RC circuit, I mentioned at the time the same thing. So if that was 100 volts peak there, then this would occur when it was at 70.71 volts peak, right? That is a very special thing, and that'll be one of our next lectures. Maybe we'll see how fast we can go through all of this, but I want to end up with a discussion about decibel attenuation and decibel amplification. And you'll see that 0.7071 and 70.71, like we've got there, is a very special place in both a low pass filter and a high pass filter and a band pass filter and a band stop filter, which are the 4 different filters. So that is a special frequency, isn't it? So that's the second one that we're going to have, and we know at that frequency that we're going to have these two things equal. We know what that frequency is now. If I had to find out what the voltage drop was across there, what the voltage at A is, because we can see the voltage at A here is 12.47, right? Oh, wait a second, I've got to break for a second. I was waiting on a call, and it looks like they have called me, and I have to get this on pause. Just a second.